In this video, we will study a particular class of problems in the field of restructured interaction, the so-called axial flow problems. As a reminder, in the previous video, we considered the dynamics of a solid according to a mode, which gave a boundary condition for the fluid. We obtained the pressure field as a sum of terms proportional to the acceleration, the velocity, and the displacement that we had to project on the considered mode. In the particular problem of axial flows, the velocity is parallel to the interface and the displacement is perpendicular to the interface. We have this in the case of plates or membrane of large dimensions in flows, but also in all problems of pipes with internal flow. We'll study the case of the pipe in tutorial class, going up to the numerical resolution of the coupled system equation. In this video, we focus on the first case. For this example, we consider that the surface is the tension membrane. The tension is noted N, and the surface density of the membrane is noted mu. The flow velocity is U0 directed along EX and the displacement psi along EY. The classical equation governing the dynamics of a membrane is given here. We recognize an inertia term, a stiffness term coming from the tension in the membrane, and a right-hand term coming from the pressure fluctuation, hence the presence of the term minus P0. The membrane being considered infinite, we do not have a characteristic length based on the geometry. We can construct one from the mass per unit area of the solid and the density of the fluid. This length can be seen as the thickness of the fluid that has the same surface density as the membrane. A characteristic time can also be constructed from the problem parameters. We can now scale the membrane equation and keep only the first-order fluctuations. We obtain a dimensionless equation which does not depend on any parameter. In particular, we notice that it is a classical wave equation for strings and membrane with a propagation velocity equal to 1. This can be understood by remarking that eta over tau is precisely the wave velocity in the membrane in meters per second. We now have a problem which consists in looking for the pressure field P' in the fluid flowing at the velocity UR, following a displacement psi' along EY. Note that UR is the only parameter of the problem. This comes from the particular choice of the characteristic length that we made. Let us resume our linearized kinematic condition in the general case obtained in a previous video. In this particular case, the velocity field is homogeneous and the term gradient of U0 cancels. The normal being equal to EY, gradient psi' scalar N0 becomes d psi' on dy. The normal velocity at the interface becomes simply d xi' on dt. And the last term is also simplified by being written minus ur d xi' on dx. Let us reposition the problem. We have to solve the Laplace equation for the potential psi' with the kinematic condition at the interface at y equals 0. We will look for solution of this problem in the form of a propagative wave of wave number k of frequency omega and of amplitude psi0. Any displacement of the interface can be represented as a combination of these wave solutions. The boundary condition at the interface is then rewritten for this elementary wave. Since it must be satisfied whatever x and t, we look for solutions for psi' in a form with separate variables where the dependence in x and t is the same. Psi' is thus equal to a constant time ei kx minus omega t times a function of y. The resolution of the Laplace equation is therefore only for f, and the solution is the sum of two exponential functions. We forbid the potential to diverge at infinity, which leads us to keep only a solution in exponential of minus absolute value of k times y. Only the constant remains to be evaluated using the boundary condition at y equals 0. Here is finally the solution for the velocity potential. Now, we need to use the unsteady Bernoulli equation to calculate pressure. The pressure at y equals 0 is proportional to psi prime and appears in the right-hand side of the wave equation. The two other terms can be put in an equivalent form, and all these together gives the dispersion relation of the coupled system, which links the frequency to the wave number. We recognize in this equation, first of all, the terms that are due to the dynamics of the membrane. The other terms are due to the interaction with the fluid. There is a term proportional to minus omega squared, the equivalent of an added mass. A term proportional to minus I omega, which is added damping, and a term that does not depend on omega, which is added stiffness. Let us now study the solutions of this dispersion equation, starting first with the case of a membrane with no fluid. We therefore remove all the terms coming from the fluid from the equation. The study of the wave propagation in the medium is done by varying the wave number k, considered real, and by calculating the values of the corresponding frequencies omega. In this simple configuration, we can easily see that for each value of k, two values of omega are possible, either plus or minus k. Two waves coexist for a given value of k, one with a phase velocity 1, the other with phase velocity minus 1. Thus, whatever the wave number or equivalently whatever the wavelength, the waves propagate at the same speed, one towards the upstream, one towards the downstream. Let us now consider the case of an interaction with the fluid at rest, that is, UR equals 0. The added mass effects come into play, and it is larger when the wave number is small. The term in 1 on absolute value of k tends even to infinity when k tends to 0. The frequency no longer follows a linear law, and the phase velocity tends to 0 for k tends to 0. The upstream and downstream waves have the same phase speed but are slowed down. On these animations, the color levels represent the velocity according to y in the fluid. White is a maximum, black a minimum. We can see that for the smallest wavelengths on the right, a smaller layer of fluid is moved by the propagating elastic wave. The effect of added mass is therefore less important. Now, what happens if the velocity of the flow is no longer 0? Let us look at the case UR equals 0.8. We can see that the waves propagating upstream are slowed down, and that in a range of values of wave number around 0, the direction of propagation of the upstream waves is reversed. Consequently, no wave goes upstream. This can be seen in the animation for k equals 0.25, where both waves propagate to the right. Let us increase the velocity of the flow a little more. Let's take UR equals 1.2. Something remarkable appears. For certain values of the wave number, the frequencies are no longer purely real. They have an imaginary part drawn here. And we still have this range of wave numbers where no information goes up the flow. But this is no longer centered on 0. A new wave number range appears around 0. For this one, we observe that the phase velocity becomes greater than 1. The waves are accelerated, and at each wave number, one of the frequencies has positive imaginary part, giving rise to a wave damped in time, and the other has a negative imaginary part, which leads to wave amplified exponentially in time. We have just highlighted an instability of the medium. By looking for the value of UR for which the discriminant of this polynomial in omega cancels, we find the critical reduced velocity for instability URC equals 1. Before concluding, let us summarize the phenomena we have just highlighted in this study of the interaction between elastic waves and an axial flow. The presence of a fluid adds inertia and slows down the waves, especially for long wavelengths. For a fluid flowing with UR less than 1, the upstream waves are slowed down to the point that their direction of propagation can even be reversed. This is what happens for long wavelengths. And finally, when the reduced velocity is larger than 1, we highlight wave amplified in time, the medium is unstable. During the next 2 tutorial sessions, we will continue the study of the interaction between a slender solid and an axial flow by looking at the pipe with internal flow. This will be an opportunity to study again the stability of waves in a system with slightly different properties, but also to look at the finite length system, which can also become unstable. Rather than unstable waves, we will show unstable modes by numerical analysis.